There are moments in science when a single observation changes everything, not with a bang, but with a whisper. On October 23, 2025, an international research team led by Marta Sewilo from the University of Maryland published a study that barely made headlines. No press conference, no dramatic announcements, just a simple publication in a scientific journal. And yet, this discovery could redefine our most fundamental question: are we alone? The James Webb Space Telescope has found organic molecules in another galaxy. Not just any molecules, the exact chemical building blocks from which life on Earth emerged, in a star system 160,000 light-years away from us. In an environment that, according to all previous models, should be too poor, too extreme, too hostile to produce such complexity. To understand why this discovery is so extraordinary, we need to talk about metallicity. In astrophysics, we call every element heavier than helium a metal. Carbon is a metal, oxygen is a metal, nitrogen, phosphorus, all metals in our terminology. These heavy elements don't form during the Big Bang, they're forged in stars over billions of years. When stars die, they distribute these elements throughout space. New stellar generations inherit this wealth. Our sun is a third-generation star, rich in heavy elements. Earth, our bodies, all life, we are products of this cosmic enrichment. The Large Magellanic Cloud, our neighboring galaxy, is different. Its metallicity is only 50% of our Milky Way's values. This isn't just a number. It means that half the chemical tools we take for granted are missing there. According to our models, organic complexity in such environments should be drastically reduced, perhaps impossible. And this is exactly where the story of ST6 begins. ST6 is a protostar, a star in its first minutes of life, cosmically speaking. It lies embedded in a massive cloud of dust and ice in a star-forming region of the Large Magellanic Cloud. The JWST pointed its mid-infrared instrument at this star. Infrared sees through dust, revealing the chemical signatures of frozen molecules. What the team found was unexpected. Methanol, ethanol, methyl formate, acetaldehyde, acetic acid. These molecules aren't simply organic, they're functional. Methanol is a building block for amino acids. Ethanol is a solvent essential for prebiotic reactions. Acetic acid, the main component of vinegar, had never been conclusively detected in space before, until now. And they all exist in frozen ice around a star, in a galaxy that should be too poor to produce them. Marta Sewilo and her team wrote cautiously in their study, "This marks the first confirmed detection of these molecules outside the Milky Way." But between the lines, something far more radical emerges. In 1953, Stanley Miller and Harold Urey conducted an experiment that appears in every textbook. They simulated the early Earth's atmosphere: methane, ammonia, hydrogen, water. They discharged sparks into it to mimic lightning. After 1 week, amino acids formed, life from chemistry, spontaneously. What textbooks often omit: the experiment worked under almost any condition. Change the atmosphere, change the energy source, change the temperature. Organic molecules form again and again. The chemistry of life isn't fragile, it's robust, almost aggressively robust. And yet we've assumed for decades that it needs special conditions: metal-rich environments, stable stars, protection from radiation. The Large Magellanic Cloud is none of these. Its stars are young, violent, ultraviolet radiation floods the interstellar space. ST6 lies exposed in this cosmic storm, and still, the molecules are there. There's something the team doesn't discuss, but every astrochemist thinks about. Complexity correlates with time. Simple molecules form quickly. Carbon monoxide, water, ammonia, these are the basics. They emerge in young gas clouds within 1,000 years. But the molecules around ST6 are different. Methyl formate is an ester, a compound of two smaller molecules. Acetic acid is a carboxylic acid, a functional group that drives chemical reaction chains. These molecules need time, complex pathways, catalysts. The region around ST6 is geologically young. The star itself is barely born. The timescales don't add up. Unless, and here it becomes quiet in scientific circles, unless organic complexity isn't the end product of a long evolution, but the starting state. What if the universe doesn't slowly converge toward organic molecules, but begins with them? Let's follow this thought. If organic molecules spontaneously form in a metal-poor galaxy under harsh conditions, then they're not the result of rare cosmic accidents, they're a property of chemistry itself, universal, inevitable. Every star-forming region, every gas cloud, every ice grain around a comet, all potential breeding grounds for the building blocks of life. The Fermi paradox asks, where are all the aliens? Perhaps we're asking the wrong question. Perhaps we should ask, where does life not emerge? The data from ST6 tells us the chemical prerequisites are everywhere. In our galaxy, in other galaxies, in metal-poor, radiation-soaked young stellar systems that we previously thought sterile. The seed is sown every... Marta Sewilo's study and her team's work is 30 pages long. Technical, carefully worded, it doesn't claim to have found life. It doesn't even claim that life is likely. But it shows us something perhaps even more important. The universe is not mute. It speaks a language we're beginning to understand, a language of carbon, oxygen, nitrogen, a grammar of complexity. And if this language is spoken in the most inhospitable corners of the cosmos, what does that mean for the quiet, stable, metal-rich worlds out there? The answer lies 160,000 light-years away, in an ice cloud around a dying star. And it whispers, "You are not alone."